Hello, this is a video to go over the notes that we took in class on simplifying square roots. So you can either watch this if you're absent, or you can watch this in order to review over how to simplify square roots. The first part of the notes we talked about just general radicals, like the cube root of 125, and just some different vocabulary parts that are on each part of the radical that we sometimes refer to. This 3, these are called your index. And if there is no index, then the index is a 2. So like on square root, the index would be a 2, since we don't ever write the little 2 there. Some other parts would be this part here. This is the radical symbol. And then we have the radicand. That's what's the number that is underneath, whatever is underneath your radical symbol. That's called the radicand. And the entire thing here we refer to as the radical. So the whole component, that's your radical. So when we're simplifying radicals, what we're looking for is if there is any hidden perfect squares within the factors. So a square root of 50 is not perfect, so therefore we can only simplify it. We don't want to change to a decimal. It would be like 7.0, some irrational number. So we want to make sure that we're just going to simplify it by not changing it to a decimal, but finding factors of 50. So that's when we made our factor trees. So you go ahead and make a factor tree for it, and that would give you a 2 and then 2 5s. So these are your ends. We rewrite 50 using our prime factors. So all as a product of the prime factors. So that would be 2 times 5 times 5. And when you're looking at it, we're looking for perfect squares. This here, groups of 2 and square roots is kind of what we're kind of gunning for, but this would be square root of 25, which is just 5. So this actually simplifies out of the radical. So this would be 5, the square root of 25, which is really 5, and then the 2 stays underneath. Something that's important when we're doing these is to note that these two expressions are equal. This one is simplified, and this one is unsimplified. Just know that they're equivalent to one another. If you punch this in the calculator, you're going to get the exact same answer as if you punch in the square root of 50. So I'll do the other examples that we did in class. Square root of 72, and then 2 times the square root of 150. So for square root of 72, do the same thing. We're doing factor tree, 8, 9. We're going to keep breaking down the numbers until we have only prime factors. I kind of circle all the prime factors. I like to put them in order from least to greatest, so I have 3 2s and 3 3s, 3 2s and 2 3s. And this product here should equal 72. So if I do 2 times 2 times 2 times 3 times 3, that's going to be 72. You gotta make sure sometimes we kind of forget them. So looking at it, I can kind of think of this as 2 ways. I would circle groups of 2. So we're talking about the first group is really the square root of 4, which is 2. The second group, this is really the square root of 9, which is 3. So both of those are going to simplify out of the radical, and what's left under is just a regular 2. This one doesn't have kind of a match. Everything here is multiplication, so this is going to multiply to 6 times root 2. 6 root 2 will be another way to say that 6 times the square root of 2. All of those are kind of the etiquette. Now you can look here, you can actually combine all 4 of these into, let's see, 4 times 9, 36. The square root of 36 would simplify to 6. So you can group them as one big perfect square or 2 smaller perfect squares. Okay, let's do this one here. So 150, 10 and 15, 5 and 3, 2 and 5. So that 2 is just 2 times. So we're only going to do our factor tree on what the radicand is. So we have 1 2, 1 3, and 2 5s. And we have only one perfect square. It's 25 right there. So the 2 on the outside is just going to be all multiplication. So it's 2 times square root of 25, which is 5, times root 6. When I can go ahead and multiply these together if they don't have a pair. So then this is just going to simplify to 10 root 6. So again, this expression is equivalent to this. It's just this is in simplest form. There's no perfect squares that we can factor out. All right, the last 2 ones that we did in class were on some monomial terms, meaning that we also included some variables within it, not just numbers. It starts out the same way. We're going to do a factor tree of 108. So that could be like 2 and 54, 9 and 6, 3 and 2, 3 and 3. So when I rewrite it, I can rewrite this as 1, 2 2s, and 1, 2, 3 3s. So once I get here, I have x to the 4th and y. I'm just going to expand everything. And I'm still looking for groups of 2 or perfect squares. So there's one. There's another one. Again, you could group them all together. That's 36. Or you can group them as 2 smaller perfect squares. And there's also 2 groups of 2 x's. So just as a side note, when you have the square root of x squared, it's x. Because x times x is x squared. So just be mindful that when we circle this is really going to turn into the square root of x squared, which is x. That's going to be another x on the outside. So this is square root of 4 is 2, square root of 9 is 3, square root of x squared is this is going to be x. That's also going to be an x. And what I have left is 3y. And then I can go ahead and combine these terms together as well. This will be 6x squared times the square root of 3y. So with these monomials, you kind of be able to start, not always necessarily expanding, but it never hurts to expand, circle up groups of 2 for square roots. The last one that we did during class was we did this one. This is actually 16. Hopefully you know the square root of 16 is just 4. We don't even need to make a factor tree. If we did, we would have 4 2's, which would then simplify out to that. So now if I just kind of look in here, I'm going to have 8 p's, 1, 2, 3, 4, 5, 6, 7, 8, and then 5 q's, 1, 2, 3, 4, 5. So you probably already know, because there's 8, I'm going to have 4 pairs, and then I'm going to have 2 pairs of q's and 1 q left over. So when I take it out, I'm going to have 4. That was the coefficient, and then 1, 2, 3, 4 p's, p to the 4th, 2 q's, q to the 2nd, and the only thing that was left underneath was the square root of 2q. Excuse me. All right, that's all.